So let's get started. Hello, everybody. Welcome to today's CITA seminar. We are excited to have Mohammad Safarzadeh joining us virtually today. Mohammad is a NASA postdoctoral program fellow at the Goddard Space Flight Center. He previously held postdoctoral positions at Harvard Center for Astrophysics, at UC Santa Cruz and Arizona State University. He did his PhD at Johns Hopkins in 2016. And today he will be speaking about the astrophysical context of gravitational wave events. So Mohammad, whenever you're ready, please take it away.
Me. Okay, you see my screen?
Yeah.
Okay. Thank you very much for the invitation. And I was planning to speak about a completely different topic, but today I'm going to talk about what I've been working in the past year or two. And I'll start with a deep dive into the core question. The question we're trying to address is the difference between the black holes that are discovered through electromagnetic waves and those that LIGO and Virgo collaboration find. So if you look at the mass distribution of black holes that are detected prior to gravitational wave events, we see that most of them range from between 5 to almost 20 solar masses. However, in gravitational waves, when we look at the sky through gravitational waves, we see a wider distribution, and definitely more massive black holes have been discovered since. And this is not just black holes, it's also neutron stars. For example, we have a detection of 190425, which is a binary neutron star with a total mass of 3.4 solar mass. And however, this stands about more than 3 sigma away from the distribution of total mass of binary neutron star systems that are found in electromagnetic observations. Now, the question is, why is there a mass difference? And if we step back a little bit, and look at just how the universe has been evolving from Big Bang, we know that stars in the structure has been forming at very high redshifts, and this has been going on through a hierarchical structure formation. And the hierarchical structure formation matters because, well, first we know that what we are observing currently by gravitational wave detectors are all the systems that merge in the local universe. So the first question is, when did these systems form that they merge now? Is there a short delay time between their formation and merger, or is there a long delay time? And this matters because through hierarchical structure formation, we know that the universe becomes more and more metal enriched through the ejection of metals when through supernovae. And we know that also at high metallicities, stars lose a lot of mass through their winds. So a star of a given mass at 2 different metallicities will leave behind 2 different black holes after the supernova explosion. The more metal enriched one will leave behind a less massive black hole because the star has lost most of its mass through wind loss at higher metallicities. So it's a little bit complicated. And the question here is whether the whole difference that we see, is it all about the formation time? There are different approaches that one can adopt. However, one should be careful about some biases that we have. We know, for example, electromagnetic discoveries are always limited by the brightness of the source, and our surveys are always magnitude limited. However, the gravitational wave approach has different limitations in terms of the mass of the source. We are limited by the mass, and we are Hubble limited in the sense that we only see systems that merge within a Hubble time. So these are important constraints, so that we have to always remember when we want to have an interpretation of the systems we observe. Moreover, we know that gravitational wave detectors are all sky surveys, and unlike our deep surveys in electromagnetic waves that we can pinpoint the position in the sky and do a long integrated observations. And what we have in electromagnetic waves are basically pretty sounds, because at the moment our observation of gravitational waves fall into human audible range. But on the other hand, we have basically pretty images when we look at the sky through electromagnetic waves. And this reminds me that perhaps it's better to say that the universe as we listen to is different than the universe as we see. And I will say that, okay, now we want to test different theories about the formation and what is the best way to proceed. And I will always, the point of this talk is that I will argue you have to combine both knowledge, both approaches to get the holistic picture of what is going on in nature, basically. Otherwise, we're going to have a biased interpretation, which is incorrect. So three things that we need to understand are metallicity evolution, formation channels and their delay times, and the physics of gas accretion. These things will impact the basic things that we have to understand in order to have a model to predict the mass distribution of compact objects that we see in gravitational waves. To start, I will focus on the formation channels and delay time, a very quick introduction and a small part of this talk. Broadly speaking, the formation channels are divided into field binary formation, where two stars start from zero-age main sequence. Two zero-age main sequence stars evolve through a so-called common envelope scenario, in which the stars lose their envelope, and the distance between the two progenitor stars shrink as a consequence, and then they become enough close to each other that when after two supernovae explosions, they are close enough to each other that they can merge within a Hubble time. And there is maybe thousands of papers on arXiv to read about different variations of this mechanism for different masses of binary compact objects. And the other scenario is, of course, the binary single interaction in dense environments, either in globular clusters or galactic nuclei. And different mechanisms have different predictions, of course, for the global statistics of compact objects. And one of there's two ways that I will briefly talk about today are the studies in the effective spin distribution and delay time distribution. And effective spin refers to the projected spin angular momentum of the binaries onto the angular momentum vector of the binary. So it is a mass-weighted spin projection of the compact objects in the binary onto the angular momentum axis of the binary. And different models predict different distribution. For example, in a dynamical assembly model in dense environments, the two black holes come together with no regard to the spin orientation of the other ones. So the expectation is that as the hierarchical merger happens, the spin distributions remain symmetric around zero and grows with mass. That is the simple prediction of dynamical assembly. However, in field binary formation, it is expected that components of the binary will tend to be aligned with the angular momentum vector. And so either different models predict either zero effective spin or positive effective spin. If we believe in this, it's a very simple first order approximation, of course, of how these models predict the distribution in a spin. But if you adopt this, you can go back. This is a work that I did in the first 10 binary black holes that was released early on in '01. One can have a look at the distribution of effective spin of the black holes. So for each binary black hole, there's a PDF of the effective spin. And by considering this and knowing the detection bias, you can get a sense of whether there is a support for symmetric distribution or not. Basically, how much support do we have for negative effective spin or chi effective? And what I concluded back then was that it is not only non-negligible, but also points to the fact that perhaps dynamical formation perhaps dominates the formation scenarios. But this is not the only way you can go after the formation channels. We know that. Yes.
Sorry, could you go back to the last slide really quick? I just have a quick clarification question.
Yes.
Yeah. So those constraints on the effective spin parameter, do those include the prior, including the detection bias within them, or do they not include the prior, including the detection bias?
In order to infer anything from the chi-effective distributions, you have to take into account the detection bias. If you remove the detection bias, yes, that's what I meant.
Yeah. Sorry, apologies. Yep, thank you.
But there is a delay time distribution is another factor, and that is a simple relation that the time it takes for a binary to merge scales as their separate same major axis to the power to the fourth power. And if you assume that binaries are distributed logarithmically in separation, for example, dNdA goes as a to the minus some power, that will translate into the delay time, dNdt, to go as t to the minus some power. And this slopes, the power law slopes, or the minimum time for delay time, is related to the slope you consider for the separation and the minimum separation that you assume for your population. Okay. The least complicated scenario to form, to model a delay time is basically these two parameters, tau min and gamma, which is like how steep is the distribution and what is the minimum delay time. For example, if you have the black line showing the formation distribution or formation rate as a function of redshift for your system, it can be any binary compact object, different assumptions about delay time parameters, slope and the minimum time, will predict different merger rate as a function of redshift. If you're more delayed, you will get like green lines. If you are less delayed, you will get the merger distribution that is more close to the blue lines, etc. And then the question is, can you distinguish?
I had just a quick question. So you have these two channels to make your tight binaries. And to me, the dynamical channel will often give you a binary with a large eccentricity, whereas the field one will give you a sort of circular binary. And your delay time doesn't mention the eccentricity at all. And
that's true. I said the most simplest. Yes, that's true.
Okay. It's like I've been doing this.
And then I will argue that even this is enough complicated
to do it. But like if you start with some.
Absolutely.
I mean, it's really like the pericenter is super important.
It's true. The including the eccentricity distribution will also be another factor, and I don't know like how it is going to affect it. It's going to push a little bit towards the short, so it's going to give a little bit of weight towards short delay times, but I don't know exactly how it's going to change the PDF of the merger time. Yeah.
But I mean, I mean, a simple calculation shows, you know, like you can make the delay time 100 times shorter or even more by starting with the same A, but a much, or even a larger A, but have it be eccentric.
Yes,
it makes a dramatic difference.
Absolutely, absolutely correct. Yes. And also, I mean, then the question, you can also get eccentric, of course, binaries in field formation scenarios through kicks, but then that becomes a very uh, a topic that not everybody agrees about. Like people have completely different opinions about the importance of kicks, or whether it is related to only neutron stars or only black holes. It becomes complicated, but I agree that the eccentricity will change the picture. But now I will discuss that even these two, constructing a delay time with two parameters is actually this one is even super hard uh, to get at, in the sense that I will describe next. So let's imagine this is the different plausible universes that you have, and you want to tell these curves apart. And one way to do this is by looking at the host galaxies of these events, if these events produce electromagnetic counterpart, for example, like in a binary neutron star merger, right? So if you look at the host galaxies of these events, we know from galaxy formation that some galaxies are red and some galaxies are blue. And these galaxies have had different star formation histories. We know that the red galaxies have formed at high redshift, and since then they have used all of the gas supply they had for most of their stars, and they have been dormant for a long time. Unlike the blue galaxies that have more continuous star formation, and they are younger systems on average. So now you have these formation channels. So in order to predict the merger distribution of a class of binary compact objects, what you do, you convolve your formation redshift with a delay time distribution, and then you get a merger time distribution. And you can see that convolving the blue and a red with a given delay time distribution will predict different distribution of mergers as a function of redshift. Maybe one example would be the following. Like imagine in the local universe, which is where all our observations are confined to, let's imagine that we see binary neutron stars only merging in red galaxies. Let's imagine we lived in such a universe. Now we know that they are dead systems. They haven't been forming the stars for the past many giga years. If you only see most of your binary neutron stars merge in red systems, that means that the delay time is long, because they are forming. The scenario, the explanation would be that they are forming in all systems, but they're also forming in blue system, but it takes long time for them to merge. That's why you don't see them in the local universe to happen for these systems to merge in blue systems. But since delay time is long and these systems, the red systems, have formed in the early universe, now you can see them merging in such systems in the local universe. I hope this makes sense, but it's very simple. If it doesn't, if I'm not clear, let me know. I'll explain further. Now, let's imagine that we live in a universe with a particular delay time parameters. Let's imagine we have a T min and a gamma. And let's imagine the universe is such that the yellow dot is the parameter of the true parameter of your binary compact object, right? Now, by observing different number of host galaxies, like how these systems are merging in different galaxies and what are their hosts, you can get closer and confine this further, like get closer to the yellow dot. For example, if you only observe 30 systems, this is the confinement, this is the posterior distribution you get for T min and gamma. If you observe 100 systems, you get the tighter constraint, and you get 300 systems, then you get a really tight constraint to within 10%, 10 or 20%. So you kind of need hundreds of these binary neutron stars with electromagnetic counterparts to be detected in the local universe, so that you can go after the delay time distribution parameters in its simplest form to the accuracy of 20%. And currently, we only have one detected system with its host known, right? 170817. And this kind of shows you like how hard and difficult this is to actually go after delay time distribution, which sets actually everything about how these systems merge over across redshift. There are different ways that I have discussed in various different papers about like, okay, how can we go after this through observing a stochastic gravitational wave background or different approaches to the host galaxies, but all of them point to the fact that we are not yet there to actually constrain in the simplest form the parameters of the delay time distribution. So that's enough for this. And then let's go to the next chapter of this talk, which is basically I want to talk about metallicity evolution or gas accretion physics, because I told you guys that the mass scale of a black hole depends on this progenitor's metallicity, so that we know. But also you can make very massive black holes by gas accretion. That also we know. So now the question is, what is happening in the universe? If we see a massive system, how can we tell apart if it is formed from a low metallicity progenitor, or is it formed from a high metallicity progenitor but has been accreting gas? Okay, so let's go to the single event that has been observed. The most massive binary black hole that I will talk about is a system that was found in the first observation of the first half of the third observing run. But let's I will start this by showing what was expected for black holes, what was expected for the mass function of black holes. So if you plot the mass of black holes or the mass function of black holes, there was an expectation that the black hole mass spectrum is going to cut around 40-50 solar mass, and due to a process called pair instability supernovae. And the process is that you have a photon, and this photon will create pairs of electrons and positrons in the presence of a nuclei. And this is detrimental to the future of a star because, for example, if you're 160 solar mass, shown with the yellow line, and if you plot this evolution of such a star in density, temperature of the core, you will see the star evolves, but it will hit an island of instability where the adiabatic index falls below 4/3. And so what is happening are two things. One is that we have to note that the temperature at which this happens is about 10 to the 9, but in order to produce a pair of positron and electron, you need about 10 to the 10K Kelvin. And now the reason this still happens at 10 to the 9 Kelvin is that all these photons belong to the tail of the Planck distribution. So that is why you still get it at 10 to the 9. What happens is that you have a pair production. These pairs are not relativistic. They are basically like dead weights. And they basically remove the radiation support from the core of the star. The star shrinks due to the heavy weight of the star. The core shrinks. This shrinkage leads to boost the temperature higher, but this is again not going to work because then you produce even more pairs. So again, you produce more pairs, you reduce the pressure support, and this is a bad cycle which leads to a runaway process, at the end of which the whole star explodes. So this pair instability issue will result in black holes of having basically black holes with maximum mass around 45 solar mass to be born from a single star. People were very happy in the by analyzing the first 10 black holes of LIGO discovered in the first observing round. And what was discovered was that, oh, there is about a maximum mass above 41 solar mass. Stan Woosley and collaborators are correct. There is a maximum mass, but soon after this was challenged by the discovery of 1905-21, which is a 85 solar mass and a 66 solar mass. So both of them are in in the outside the pair instability limit. People originally argued that both of them are assembled dynamically, but there are many issues with assembling dynamically each one of these black holes, because when you do assemble black holes this way, the resulting black hole will receive a kick, and it is hard to confine both black holes in a system and then again bring them together to make a more massive black hole. So this is a very fine-tuned scenario if it had been forming dynamically. What we suggested with Zoltan Hyman is that we have a binary system, and both black holes are about 40-50 solar mass when they are born, but there is a gas inflow and where they reside, and they accrete through Bondi-Hoyle accretion. And this can easily happen in the core of atomic cooling halos at high redshift, which are very, very dense systems. So what we showed with Zoltan Hyman is that if you have a binary black hole, and if they reside, for example, within 0.1 parsec of an atomic cooling halo, you can actually double their mass in a matter of percent of a million year. Or if you are within a parsec of at the core of the atomic cooling halo, within 10 million years, you can actually accrete enough to double their mass. So this is helpful, and we said that look, we don't know the delay time for these systems, but we played around with different plausible delay times, and all of them showed that if you assume these systems are born from population 3 stars that are shown with black line, the merger times which are shown with colored lines all predict a rate that is consistent with the observed rate of such systems. And we said, okay, so this is still a plausible scenario. And later on, in 03, the black hole, due to discoveries of such systems, the black hole mass function was revised, and now it easily extends to 100 solar mass. And the question is, can we explain the observed black hole mass function? And work that I did with Enrico Ramirez Ruiz is that we assumed 5% or 20% of black holes that are formed in the early universe to double their mass through gas accretion. And what we show here is that the black line with its with shaded region matches the dotted region. So the dotted region is the mass function, the observed mass function, and the colored ones show the our model. So what we show is that the black line in our model is consistent with the observed black hole mass function if at least 5% of the black holes that are formed at high redshift double their mass through gas accretion, which was interesting. So, however, there are issues with this scenario of gas accretions into binary black holes that they require further simulations of gas accretion into binary black holes that we are working on. But the issue is not just the massive binary black holes. There's also the most massive binary neutron star that I referred to in the beginning of the talk, and that is 190425 with a total mass of 3.4 solar mass. Now, this is a different system. We are not sure if this can be formed through gas accretion, but let's talk about some plausible scenarios. So when this system was formed, everybody was shocked, and people had different ideas. And one of the ideas of the Lagos paper out was that that this system has been born as an ultra-compact binary pulsar. And this is why it has been previously missed in radio observation, because this, due to being in a compact binary with very short separation, the detection of the pulses of the pulsar are smeared out, and this is very hard for the observers to detect such systems. The implication of this is that such binary neutron stars are born, of course, with short separation, but the implication is that they merge fast. So the delay time is very short. Now, okay, so why can this not be a good explanation of the system? The reason that this is perhaps wrong argument is the following. We know that due to the wind mass loss that changes with metallicity, more massive neutron stars can form from less metal-enriched stars, progenitor stars. So if you want to make a massive binary neutron star, you better be forming them from a low mass progenitor. But this system has been observed locally, and that line of argument is saying that the delay time is short. If the delay time is short for these systems, and we know in the local universe that the metallicity is high, the chances that this system has been formed from a high metallicity progenitor is actually very high. But we know from a high metallicity progenitor, we don't get massive binary neutron stars. So that is a conflict. And if you want to make such systems from low metallicity progenitors, and if you basically invert how much a star formation in the local universe is taking place in at low metallicities, you will get very high efficiencies for such systems to form, because the formation, the star formation at low metallicities is very rare. Now you want such systems to form from low metallicities, and that would imply the formation efficiency, a very high formation efficiency of around 10 to the minus 3 solar mass, 10 to the minus 3 per solar mass. Now, I will argue in the next slide that this is insane, this such formation efficiencies. And the reason is that we have some constraints for formation efficiencies of binary neutron stars from ultra-faint dwarf galaxies. So what are they? So ultra-faint dwarf galaxies are satellites of the Milky Way that are believed to have formed very early on and ceased their star formation. Some are dead since redshift 6 or 7. And these are routinely being found in dark energy survey. And in one of them, namely Reticulum 2, we see like 7 of their stars have been observed to be polluted with europium, which is an element that is generated when 2 neutron stars merge. At least this was the leading, this is the leading theory. So this, which means that in Reticulum 2, which is a system that is dead since, let's say, redshift 6, in that 1 gigayear time life that it had by then, there has been a neutron star binary formed, merged, polluted the medium with europium, new stars formed from this gas. Now we see them in their spectra. So this gives you a constraint and formation efficiency of binary neutron stars at low metallicities, because these systems again are very high redshift systems, and we know that the metallicity back then has been extremely low, and also we know that this is the metallicity of these stars. We know it's like hundreds. So the x-axis is showing the metallicity, and the y-axis is showing the europium. So the we know that these are very metal-poor systems, but it's still enriched in europium. So this gives you the formation efficiency of binary neutron stars at low metallicities, with the implication that this has to be a fast merging channel, whatever led to the formation of R process elements in this galaxy. So we did, in 2018, I did some Zoom hydrodynamical simulation I don't show the movies because the movie, when I show it, the whole thing freezes. So I just took a snapshot of it. It's just dark matter baryons and metals, and also our process, which is generated by the binary neutron stars that we simulated in the simulation. So basically, it's a stochastic star formation scenario, and then with some formation efficiencies, we tag some of the stars as binary neutron stars, which will receive a kick with a delay time, and then when they merge, they instead of metals, they're going to pollute the medium with our process. So we do these simulations, and then look at the distribution of the stars in our process enrichment. And what we saw is that the observed ratio of our process metal porous stars to all metal porous stars is much higher than what we got from our simulation. And what we got from our simulation was assuming the most optimum yield for our process materials. And the only way for us to match the observation is to basically artificially boost the number of binary neutron stars that are formed in nature at low metallicities. Basically meaning that we needed to inject fast merging channel binary neutron stars by hand into the simulation so that we match the observed ratio. That is the message of all of these simulations. The issue, and one other issue that we need to be careful about is that binary neutron stars are born with kick velocities. So if there is no kick, this was the distribution that we found in one of our dwarf galaxies, that, for example, this is how our process material and iron are distributed in the gas. And on the left panel, how the stars are distributed in europium versus iron distribution. And overplotted are the stars of reticulum 2. So the green are the stars from simulation, and then the red are the stars that are observed in reticulum 2. But if the explosion happens off center, which had in one of the systems, this is what happens, so that the distribution of europium and iron are not concentric, then what you get for your stars is that they are not really enriched in our process as much as they could be if there was no kick, which is obvious because now our process material is too diluted before the next generation stars are born and inherit the europium. So that is why we needed the fast merging channels, because although you're gonna form and eject our process material, but you're gonna produce this our process material in irrelevant, like outside the galaxy, which is not gonna contribute to our process enrichment of the system. So this leads to some discussion about, okay, what section or what part of the parameter space in terms of delay time and kick velocity can the binary neutron stars have in order to enrich a small system like reticulum 2? And one can see like those that can enrich basically do have a very high kick velocities, but have very extremely short merging time. Those are the ones that merge inside the halo that can lead to our process enrichment. And there are scenarios that can lead to such systems, but they are not mainstream. They're not. So there is this case BB mass trans. This case BB binary formation scenario, but these are not mainstream ideas, and some people argue whether this is physical or whether this is not physical. But regardless, what we get is that we do need processes that generate extremely short period binaries at low metallicities in order to explain a satellite like Reticulum 2. Putting all of this together, what we get is the following. The R process ultra-faint dwarf galaxies, they have a range for what is the efficiency of formation of binary neutron stars at low metallicities, which is shown in yellow. The blue is the constraints that you get from the gravitational wave detection, of the binary neutron star. And the other lines are basically showing different mainstream, non-mainstream formation of short binary neutron stars. So what we get at the end is that it doesn't match. You cannot actually get to such extremely high formation efficiencies as is implied by this gravitational wave detection, specifically at low metallicities. So that challenges that interpretation. Now, yeah, okay. And then I always argue that this can be itself a good topic for a PhD, is to do actually cosmological hydrosimulation in a survey type to make sure that this is a valid argument or not. But what needs to be done? So other than doing the cosmological simulations of R process enrichment, one has to come up with other tests of the fast merging channel scenario. And also sometimes maybe we need to think outside the box. And what do I mean by that? Alternative tests, one paper that we wrote with Valeria Coral is that we said, oh, okay, so if these systems like 190425 are short binaries, LISA should be able to detect them. So that was interesting. So we said, okay, these systems is enough massive that LISA can tell them apart from their less massive counterparts. And then there was a discussion that how long it takes for LISA to detect such systems and how far they could be, and the implications of that for fast merging channels. So yes, so one can detect them with LISA, and that would be very highly interesting. The other idea that we had is that basically, could this be all about electromagnetic waves? The magnetic field of a neutron star. And what we mean by that is that if you look at the distribution of neutron stars in period derivative, you see two blobs. One is for millisecond pulsars in the lower left in the red blob, and the normal pulsars that are shown with the blue contours. There is a place called graveyard where the neutron stars spin down and go to the graveyard, and that is where they won't be detectable by radio observations. Now, one idea that we had was, could it be possible that these massive systems are actually forming relatively with high efficiencies, similar to the other binary neutron stars that we have already observed, but they have migrated into the graveyard. That's why we miss them in radio observations, and we can only detect them in gravitational wave detections. This needs to be modeled in detail in basically population synthesis model, which is again become perhaps suitable for a PhD project. But that would have a large implication for magnetic field evolution of massive binary neutron stars. So basically what the theory would be that massive neutron stars are formed such that they quickly migrate to this graveyard. And if this is the case, we have a complete bias of the distribution of pulsars in the period derivative, and with large implications. The other scenario that we advocated was that this system can form through gas accretion. So basically, the same scenario that we applied for binary black hole system, but now can this happen for these systems as well? Are these systems binary neutron stars that have been accreting gas, for example, in an AGN disk? In a very gaseous environment, they have lived there for a long time. They have been accreting gas. Could it be the case that such systems, their environment is inherently different? This will also have implications for LIGO, but we haven't started working on this one and this scenario yet. So, and to wrap up, I mean, we are stepping into unknown field. This is just few examples that I discussed today, basically two systems that I discussed today, and we will have definitely more and more systems. This the number 67 was, I guess, the number of detections by a few months ago, but now it is more than this. And more rare systems have been observed. And it is just the fact that we're going to keep observing about 50 binary neutron stars per year by 2004. That's the prediction. And who knows what we'll detect and what will be the mass distribution of binary neutron stars that we'll be able to detect by then. And some folks at CITA are working on third generation gravitational wave detectors. And we know about Einstein telescope and the Cosmic Explorer that are coming online in the next decade. And these systems are actually going to see anything that happens in the entire horizon of the universe. And so we will be basically going into 100,000 binary neutron star a year era. But I don't know if we can even have the pipeline for analysis of such observations yet. But the discoveries that await us are going to be, of course, revolutionary in nature. So, and this is how much science we could have done only by just two systems. And imagine when we hit this era, what kind of science will emerge. I'm eager to see. So at the end, I wanted to just basically talk a little bit about how different it is, like to look at these systems. And if you have this mindset of galaxy formation, chemical evolution, you saw like all of them were relevant. Like if you know about chemical evolution, you can have a completely different perspective on the suggested formation scenarios than if you don't read or think about the other electromagnetic approaches. So at the end, I think that it is always with the combination of these two approaches that we can kind of get a correct interpretation, and otherwise we will get a biased interpretation of the systems. I think I stop here and I will take questions, and I hope it was I didn't go too fast over some subjects, but ask me if anything wasn't too clear. Thank you.
Perfect, Mohammad. Thanks very much. Very interesting talk. Okay, any questions on Zoom or in the room? Norm, do you have a question?
Yeah, I was going to ask about, you sort of quickly mentioned accretion onto both binary black holes and binary neutron stars. And there was also some, sort of time involved there. You wanted to double their masses. So yes, that would be, my recollection is to double your mass on a black hole at Eddington would take something like 50 million years. That's not any kind of sort of delay time, but what, so I want to get a feeling for the accretion rates that you're looking for.
Right. So what we let me bring up the slide. Maybe this is a little. So the left panel of this plot shows how long it takes for the binary black hole to double its mass, and different lines are showing for different masses of the binaries, and it depends on the mass of the binary because, of course, the m dots just itself depends on the mass of the binary squared. But what we did is that we are assuming also here the m dot that we are getting is also depends on the environment that we are. So for the calculations that we did, the mass accretion rate was a function of radius from the core of the atomic cooling halo, because that set the density, and also its temperature was setting the sound speed of the medium. And so that's how we computed the mass accretion rate. And we compared the time for doubling the mass, and we compared that to the dynamical friction of the system, which depended on where is this black hole rotated, like how far it is from the center of the atomic cooling halo. So we basically tried to compare these two and say that, oh, okay, so if the time to doubling is less than the dynamical friction time, then this is an acceptable theory. And then what we find is that they are almost the same time scale. One issue with doubling the mass that I was referring to is that the idea is that if by the time you double your mass, you have to merge, because or in other words, people are arguing is that you can never accrete more than you cannot triple your mass before merge. If you double your mass, you're going to merge. Basically, this is the theory. But I don't believe in that, because this is very simplistic derivation, in the sense that what happens to the gas when the binary black hole is in very, very short distance is problematic, in the sense that prior to, at large separations, yes, you can accrete, and this accretion is going to take away the angular momentum of the binary, and then you shrink further and further while you're increasing your mass. But it is not clear that this process is all the way through, all the way to the merger, because at very short separations, the orbital velocity is gonna go supersonic, and now the gas that hits the binary is gonna get shock heated. To me, it's not clear that it's gonna take away the angular momentum anymore. And perhaps you can accrete from different directions, still you increase your mass, but you do not necessarily also, the gas accretion does not necessarily lead you to merging. But this needs hydrodynamical simulations, like very detailed hydrodynamical.
Well, I had an even simpler worry was, if you're accreting at Eddington, right, there's a lot of feedback on the gas. And Bondi-Hoyle accretion isn't going to work.
That's the amount of accretion. So there are, when I was writing this paper, I read a lot about this. And so my understanding is that it is divided. So there is a feedback that you have, and you're going to stop the accretion. But again, it's like a phase that you have to wait it, and then it can also be overcome. So if you go to if the accretion rate is about 500 Eddington, then you can just accrete again with no problem, as the photon itself is going to be also accreted. The whole energy density is going to be accreted onto the system.
Yeah. So I agree with that, but I mean so you're arguing that you're sitting in the center of some halo and accreting? Is that the idea? Because if you're just in it, most of these stars are going to form in. You're talking about in dwarf galaxies? What kind of galaxies are these things forming in?
Yes. So these are binary black holes from population trio stars that have been forming at super high redshift. And the idea is that, yes, there are papers that show that including and not including the feedback is going to really impact how much mass we can accrete.
Sure.
Yes.
Okay, but you're imagining that they're sitting at the center of the halo. That's really the point here.
We are saying it is migrating around the halo around, and then it is going to dynamical friction due to dynamical friction.
Fall into the center. Yeah. Okay.
But we are saying that it can go to accretion rates above hundreds of Eddington because these systems are extremely dense at high redshift. The atomic cooling halos. That was like part of the argument, and not the whole part of the argument, but that was the contributing part of the theory that you can actually overcome this this issue. And another thing that I wanted to add is that these simulations are already done. These simulations of accretion of gas into seed black holes are already done with the aim to explain the quasars, million solar mass quasars at high redshift. And here we have even a much simpler ask. We don't want to increase them to million solar mass. We just want to double their mass. That's all we want to do. So to us, that should be easier, much easier. And so if people have been trying and people have been writing about it, even like since 2006, that if you turn on the accretion, you're not gonna make the seeds for quasars at high redshift. But this is not what we want here. We don't want to increase them to million solar mass. We just want to double their mass. Can we do it? It doesn't seem too difficult. And the beauty of this is that you don't necessarily need to fine-tune this. And it is also possible that you relax the binariness of it and just grow each one of them individually and then merge them together later on. So you can actually accrete to two individual halo black holes in atomic cooling halos and then bring them together dynamically and merge them. That is possible. That is plausible, but and some people like that scenario better, but I'm not sure how much fine tuning would be involved in that scenario. But to me, this increasing or doubling the mass before the merging doesn't seem too fine-tune of a scenario if you adapt it through gas accretion in atomic cooling halos. This is a short answer. Yeah.
Thanks, Mohammed. Was there another question from Chris? Do you still have your hand up?
I was mainly going to ask the same thing about feedback. I guess when it comes to photon feedback, you can overwhelm it. But there are these, if you add magnetic fields to the mix, it can become more complicated, I understand. And so you can get inflow-outflow solutions and also, the energy extraction directly from the black holes. So it's not obvious that you can just dump material onto them. But I think also when it comes to accreting material, even if you ignore feedback, it makes a big difference whether the gas you're trying to accrete is rotationally supported, has more angular momentum than the binary or not. So if it does, then you're doing gas accretion through a disk, and it's like binary star formation, which doesn't necessarily have to shrink your binary.
Okay, that's a good point. Yes.
That wasn't really a question there. Sorry.
Yeah. No, thank you for the comment.
Any last questions on Zoom or in the room? If not, let me sneak one quick one in. Mohammed, at the beginning, you gave a simple estimate, a rough estimate, maybe 300 binary neutron stars with EM counterparts in order to distinguish the fraction, yeah, exactly, of field formation versus dynamical formation. I'm just wondering, is 300 a little bit pessimistic? Because can you not do some sort of statistical association between the sky localization, the distance measurement, and the host galaxy? Does that sort of thing buy you anything? Do you really need the EM counterpart in all cases?
So we wrote a different paper that just used the scaling relation of the host galaxies, and we got about the same answer. So any way I tried it, it's very pessimistic. I wrote 4 papers on this, and even with 3rd generation is extremely, I wasn't getting really good results. I mean, okay, 3rd generation gravitational wave detectors, of course you can do a lot to them, but even then you need like a year-long observation to pin down different formation, different delay time distributions, because again, the error on the redshift of the source, although you detect them at high redshift, but the error bar on the redshift is going to also explode with redshift. So you need a lot of observation and integration time for 3rd generations to actually even do it by them. So whether you can add more information to this, perhaps you can add more information. You mentioned the sky localization. Is that what you're saying, that there's extra piece of information?
3D localization. Yeah, 3D localization, statistically associating it with the host galaxies that are in that area.
So are you worried about the kicks? Is that what you're worried about? Like, so that the kicks are gonna know? Are you talking about just like basically 2-point correlation function of this distribution?
Yes, that's exactly. That's all I'm saying.
So I think that is exactly. I'm not sure why it should give you a better result than just looking at the scaling relation of the host galaxies, because these theories about the host galaxies being like red or blue, these are also based on hierarchical structure formation that predicts certain scale distribution. So to me, they should give you the same result, but I haven't done the test. We're curious to see if that is gonna, if that's gonna buy you more information.
That's good. No, I was just curious
about this. Yeah, interesting. Yeah.
So I think we better stop here. Mohammad will stick around for anyone who wants to chat for a while. So let's thank him again. Very nice talk. Thank you.
Thank you.